The guy's back again. Let's see there. Well, anyway, it's either lecture. I'll say it's either 7 or 8. I'm not sure. But anyway, we've wandered into chapter 3 now. I think we have concluded with chapter 2. And so we're moving on to more and more the behavior of electrons, and let's consider billions and billions of electrons, and let's figure out how to get them to move around and what type of situations or environments do we need to foster the motion of not just a single electron, but oodles and oodles, literally billions and billions of electrons moving all basically in unison or in the same direction, but not even that is the case because of alternating current. But electrostatics and understanding electrostatics and how do charges build up, and when there are excess charges, like loose electrons, what rules govern their behavior. And then when we have a set of rules that governs the behavior of electrons, including forces applied to the electrons, then we can revisit Newton's laws of motion. A force is being applied to an electron has mass, it's very, very small mass, but that means the electron's going to accelerate. And so we kind of, with this set of rules, I think it's like 5 rules for charge behavior. And then Newton's 3 laws of motion, we get an understanding of why electricity works the way it does. So let's get into it. Okay, so atomic nature of electricity, that does come into play. There's also some relativistic concerns, which I have a pretty good, I really like what I've dreamed, the thought model that I dreamed up for the relativistic concerns, because one of the rules of electrostatics seems to contradict the other one. And the only way to explain it is to invoke relativity of size. And so I'll get to that. Just be patient. Okay. Methods of electrification. And so how does a neutral object become a charged object? How is it that we imbue objects with charge? And it's usually either stealing electrons or swapping electrons from one material to another. And so electrons are shed by one material and then they deposit it onto another material. And then we have positively charged. The first stuff that lost electrons is positively charged. And then the stuff that gained the electrons is negatively charged. And then how do we, once that happens, then there is a risk of shock. There is a risk of static discharge, if you will. And so I have to explain grounding too. Okay. Interpret the results of various electrostatic interactions, and I hope to have time to run during the live presentation of this lecture. I hope to have time to run the Van de Graaff generator. Hopefully it'll be working that day. Hopefully we'll have a nice dry day. Yes, water vapor in the air affects the ease in which electrostatics occurs. Okay, water vapor in the air actually acts, because it's a polar molecule, it kind of acts as an insulator to charged objects. So now what the heck is an insulator? Well, we're going to find that out at the end of the lecture. Conductors versus insulators, and how are those different? And again, it goes back to atomic theory. Different numbers of valence electrons, certain materials behave differently than others. And that does play into conductivity and lack of conductivity in the case of an insulator. And then how to consistently shock someone with built up charge. And so this is a great prank especially here in the wintertime, and I'm recording this uh, just before Christmas. So, as you find yourself trapped in environments with artificial heat and you notice that your upper respiratory system is drying out and it's hard to keep things moving, unbelievable. Every time I didn't even answer. Every time I do a recording, the phone's going to ring. Okay, let's get going. So, yeah, in the wintertime, artificially heated environments, upper respiratory system is drying out. And that's because there's a lack of moisture in the air because of the artificial heated environment. So, running a electric heater or even a gas heater um, drives the water vapor out of the air inside a building. Okay. And so that removes the insulative property of inside air. And so it's a lot easier to build up static charges and conduct electricity. Now, you will need some other things, and I'm just going to get this out of the way now so we can get to the science. So, if you want to prank somebody by shocking them, you're going to need to invest in a good pair of wool socks, and you're going to need to have a carpet in your house. Okay? The carpet's going to be made out of either like hair fibers, like camel hair fibers, or could be polymer plastic fibers. It could be cotton fibers. It um, could be wool fibers. I don't think there's very many wool fiber rugs. It's usually some type of linen or other kind of grass-like material that we've made into some kind of cloth. So it's usually a natural cloth, and that's different than the wool. If you have a wool rug, first of all, weird. Uh, Second of all, this won't work. Okay, so you need the difference in material between the wool and whatever your natural carpet fiber is made out of. Okay, or polymer plastic. I think this does work on the green astroturf that you have, but of course you have to bring that inside, not out on your stoop because there's water vapor out there. So you're going to want to scuff your feet with your wool socks on across your carpet until you can start feeling the hairs on your arms stand up. Okay, wear a short sleeve shirt. Don't touch anything metal. Okay. And then, if you can stay on the carpet without touching anything metal, you will sneak up behind the person you want to shock. And I think that probably the hot target zone, the preferred target zone, is the earlobe. So get your finger right up close because we're going to see Coulomb's law, which is rule number 2, says that the electrostatic force builds when the distance gets smaller. It's inversely proportional to the distance squared, which might sound familiar to you. Okay, and so that's how all fields manifest, and that's why you hear it so often. That's why we have an inverse square law for the X-ray as well, because it's electric and magnetic fields spreading out. Okay. So bring your finger in, and you want to extend your finger and bring it in as close as you can without touching the rest of their head or anything metal. Bring it in right up behind their earlobe, and you should, when you get it in within about a centimeter or so, and you're properly charged, you should ground out your excess charge on the person's earlobe, and um, there'll be a nice snap, right? So they get the double. They get they get the actual electricity running through their ear, but then they hear that snap as the electrons jump from the end of your finger onto the ear. It makes a little crackle in the air, um, and they can hear it very loudly right there in their ear. So it's like a twofold startling. So it's really, that's the best place to shock somebody, is right on their ear if you can. So um, don't ask me how I know. Love you, sis. All right, let's get into it. Okay, so there is an atomic nature to electricity. Remember, we said when we talked about, stones and buckets of water are different. Atoms and molecules and elements and all those compounds, all those fancy words we learned in atomic theory, it really boils down to the mix of protons and neutrons and the valence shell capacity, or the availability of vacancies, or does it have a full shell. It really determines the electric behavior, or the conductivity. We'll, and we'll elaborate on that at the end too. We'll come back around full circle. But we know that electric charge, it's actually a possession of two of the atomic particles we learned. Protons have positive charges, um, and for matter, not antimatter, it is the smallest unit of positive charge. Electrons are the smallest unit of negative charge. Okay? Um, Electrons have an advantage in that they're the smaller object, and it's easier to release them from orbits around the atom. J.J. Thomson's experiment, he said they can be plucked out like plums in a plum pudding, or raisins in raisin bread, remember? And so that's where part of this comes from, and part of our understanding, which we're going to get to, is one of the rules is electrons are free to move in solid conductors, but protons are typically tethered into the nucleus, and even though they experience equal forces, electrostatic forces to the electrons, they're just too heavy to respond. The electron responds because it's lighter, it's got less mass. Okay? All right. So electrostatics is electric charges at rest, kind of electric charges not moving in a desired pathway is a better way to. So electrification, electric charges not moving is the definition of electrostatics, but there you can you have an imbalance still. So electrostatics, if this was the definition, then all neutral objects would be exhibiting electrostatics. But you don't really see the effects of electrostatics until you have excess charges or an absence of electrons. So you can stack, if you have a conductive, let's say you have a metal bar and you put more electrons on it, then that's called electrification, first of all, and then you see it behave according to the rules of electrostatics. If you have that metal bar and you were able to pull some of the orbital electrons from it, it would also be charged, but it would be positively charged at that point. So in electrostatics, we can charge materials positively or negatively, depending upon if we put extra electrons on them or if we steal loosely bound electrons from them. Okay? And so negative and positive charging of objects can occur. Okay? Now it's important to remember that that is just a convention. What? We've all agreed that the electron has a negative charge and the proton has a positive charge. Okay? That's something we made up so we can better understand their behavior. Okay? Um, and Ben Franklin actually, I think he was the one that kind of made up. He said that there was negative was an absence of this electrical fluid, and positive was an abundance of electrical fluid, and that's where, and a lot of early experimenters with electricity kind of like that description, and so we're stuck with negative and positive. He was exactly backwards. Okay. The absence of electric fluid is actually an abundance of electrons, and electrons are the ones that flow. And so, yeah, Franklin got it backwards, and we will see that that has an impact on the way you learn electricity later, and it drives Mr. Shepard bonkers. So, but those are relative terms, or just basically a human construct. We've made the parameters negative and positive. We gave it those labels. We gave it the name electron and proton. And so, yeah, uh, we all kind of we made, but there is a consistent atomic particle that we call the electron that once we assign it a negative charge, it behaves in a certain way. And then there is another atomic particle that we call the proton, and we assign it an opposite charge to the electron in order to explain some of its behavior. Okay, and so that's what they mean by relative terms. Okay, we could just as easily have made the electron positive and the proton negative, and it would work the same. The important part is the electron and proton are oppositely charged. Okay, the common convention is the electron's negative, the proton's positive. Okay. Uh, Now, zero or ground potential, most matter is actually in a neutral state. Most matter here on Earth. It is grounded out, it's in its lowest energy state, and it has a balance of electrons and protons. Okay? But occasionally things happen, forces are applied, and electrons are either removed or extra electrons are added to an atom. And then those are called ions. Okay. Now we use the term ground because literally we're talking about the ground. Okay. The ground, and I'll revisit this later, is an infinite reservoir of charge. Well, which kind? Both. What? Yes. The Earth itself, or any sufficiently larger object, larger than what? Well, larger than what you're dealing with, can act as a ground. That is, can donate or receive excess electrons to return electrified objects into a neutral state. That's the power of a ground, and that's what the Earth does all the time. It grounds out rain clouds. Yeah, you call it lightning. That is a grounding event. The cloud, because of its internal air currents, is separating its charges. It's creating ions. Once it creates enough of those, then there is a electrostatic force of that excess charge attracted to the earth, and you get in the right moment, the electrons fly down out of the cloud. They also fly up out of the earth at the same time, and it basically sets the air on fire along the pathway of the electrons. And that's what we call lightning. It also, there's so many electrons moving that it actually shears regular air molecules out of the way. Okay, think of like a high speed snow plow pushing the snow off a road. Okay, that's what the bolus of electrons coming out of the cloud is doing to the nitrogen and the oxygen atoms. And that's why we hear thunder later, is because every time there's lightning, it creates a partial vacuum, and then the air collapses back on itself. All right, sorry, lost my place. I had a little chat to give. Um, so yeah, it's an infinite reservoir of either charge. I think I was just about to wrap up here. So, and then we get into the laws of electrostatics. There's rules that these charges obey. Okay. Which is basically the meat of the lecture. This is the most important part of the lecture, are the rules that follow. All right, so rule number one. You probably have already heard this. like charges repel, unlike charges attract. And so the nucleus has protons in it, right? It has neutrons too, but they don't have a charge. The electrons are actually in orbits because of their attraction to the nucleus. Okay. Um, but they're repulsive to each other. So they're kind of set, and that's part of the stable energy states that Bohr talked about, is the combination of the attractive forces in the nucleus plus the repulsive forces of other electrons around the nucleus in the same atom. They kind of balance with it and counterbalance with each other as they all move around the atom. Okay. And so yeah, this is rule number one. Protons and electrons are attracted to each other. That's the blue arrows. Yes, those are vectors. Those are force vectors. Good. But electrons to electrons and protons to protons, which raises a question. Well, that's what the neutrons are for. But when two electrons get too close together, they actually experience repulsive forces, that is, force vectors away from each other, okay, rather than force vectors toward each other. And so the flaw is the blue line should also be a double arrow because of Newton's third law of motion, okay, because it's a force vector, okay, and forces are applied equally and oppositely. And so they did it like this because they don't want to indicate that the nucleus is also attracted to the electrons, but it totally is. It just doesn't move because it's so massive. Okay? We've already covered that. Bicycle and city bus. Right? Right. Okay. Now, that raises a question that I'm not sure I addressed in the atomic theory lecture. How the hell does the nucleus hold itself together if it's bunches and bunches of protons and they all repel each other? Well, it turns out that the neutrons serve a purpose, and they exhibit, between the neutrons and the protons, there's another force called the strong nuclear force. The strong nuclear force is the neutrons holding the protons in, okay, and the protons holding onto the neutrons. And so the strong nuclear force is able to overcome the electrostatic repulsion that would be present if it was just a bundle of protons in the nucleus. So you notice hydrogen can exist as a single proton with a single electron in orbit, okay? But helium, we have to start adding neutrons in order to get helium. So helium is two protons, but all of a sudden there's two neutrons. Why is, in the most common isotope, why is that? There is helium-3, but why two neutrons? Well, because we need to hold those protons together with something, or else they would just fly apart from each other and return and change back into hydrogen. So yeah, so the neutrons apply the strong nuclear force that overrides the proton-proton repulsive force. So why didn't they do repulsive forces inside the nucleus too, if they wanted a consistent model? All right. But anyway, you get the idea. Like charges repel, unlike charges attract. All right. Now, what is the magnitude of the attraction and the repulsion? Well, it's kind of like gravity, but for protons and electrons. We call it Coulomb's law, or electrostatic force. Okay? The force between two charges is directly proportional to the product of their magnitudes. That's Q1 times Q2. And then there's the Coulomb constant, K, and that's just it's a fudge factor. Okay? It's part of, I think it's related to that epsilon that we saw in the electromagnetic radiation. Remember Maxwell's equation, epsilon naught? I think the K is related to that epsilon naught, the electric permeability of free space. Okay, and then inversely proportional to the square of the distance between them. So as charges are far apart, the force falls off exponentially, okay, like an upside down parabola. Okay, as charges get close together, the force increases exponentially, like a conventional parabola. Okay, um, and so it's an inverse relationship, but it's a quadratic, and so it like curves out. Okay, I can draw it in class live. You can see a graph. You can probably look up a graphical representation of Coulomb's law versus distance on the internet. You'll see the shape of the graph we're talking about. Okay. What other law does this sound like where something is inversely proportional to the square of the distance? Yeah, that's radiation intensity. That's the inverse square law. Very good. So, and that's not. This is what's called a. So this is a force formula, or a general field formula. The presence of the d squared term indicates that there is an electric field present. Okay, just like gravity has a gravitational field, right? And so, yeah, the force of gravity is also inversely proportional to the square of the distance from the source. That's why it's an almost constant value, very, very close to the Earth's surface. But as you move farther away from the Earth's surface, the force of gravity starts to reduce quite considerably. Okay. Reconcile this law with Newton's second and third laws. Do atomic nuclei experience a Coulomb force? Well, is there an oppositely charged object nearby? Yeah, the orbital electrons, right? And so this Coulomb, when Coulomb designed this, is Q1 is charge or charges, number one. So you might have an individual charge like a proton, or a charged object like an iron bar that you've pulled electrons off of. Okay, so the magnitude of the charge on object one, which could be the atomic nucleus, times the magnitude of the charge on object 2. Could be a single orbital electron or all the orbital electrons. Could be extra electrons that you've somehow gotten to stay on the metal bar. Okay, so the product of all the charges involved, basically. Now, which one does the force apply to? If there's a force of attraction between the electrons and the nuclei, doesn't that go both ways? It in fact does, yes. Okay. And so, yeah, the force that is calculated here is the force. So if you have an electron proton like hydrogen, the force the electron feels is equivalent to the force the proton feels. But we see the electron orbit and accelerate around the proton because it has a smaller mass. Remember the intuitive form, F divided by m equals a. We only witness an acceleration in very, very tiny objects versus larger objects when equivalent forces are applied. Okay. In other words, electricity concerns the distribution and movement of electrons and has little to do with the positively charged protons locked within the atomic nucleus. Partially agree. Okay. Those positively charged protons sure are handy when we're trying to pull the electrons. And so I would say that it does have to do with the movement of the electrons, but you don't expect the protons in the nucleus to move. But it really doesn't have, that's the source of the pull force on the second half of the electric circuit. Yeah, you push electrons out of the cathode of the battery, but to get them to return to the battery, you pull on them with the anode positive charge. Where do you think that comes from? The nucleus. So I disagree with little to do. This could have been worded better. like when forces are equally but oppositely applied to two particles, Newton's third law of motion, one significantly larger than the other, Newton's second law of motion, mass is inverse to acceleration. We assume only the small object moves. That's a little bit more, that's a little bit closer to the, and it satisfies the why, other than protons don't move. Why? Because we said not, they don't. See how that sounds incomplete? Aren't you glad I taught you Newton's laws of motion now, so that you understand why the protons aren't moving? Okay, makes it a little bit more easy to wrap your head. Oh, it's only the electrons move, and I know why. Mr. Tilton taught me that already. Okay, laws of electrostatics. Rule number 3: distribution. Charges reside on external surfaces of solid conductors. They attempt to repel each other due to negative charges, so they distribute themselves fairly uniformly across the surface of a charged object. Okay? Now, rule number 1 was like charges repel. Okay? So, this object, this solid conductor, let's say it's a wire, because it kind of looks like a close up of a wire. So, let's say it's a wire, right? Um, what's it made out of? Oh, yeah, atoms. One of the atoms have as their external, their most external component. That is what is on the perimeter of the atom. Oh yeah, electrons in orbits, right? And so if we put extra electrons onto this wire, let's say we put them into the middle of the wire amongst all the atoms, are they going to stay there if like charges repel? And so they have to, even if we put them in the middle of the copper wire, extra electrons like injected into the middle somehow of the copper wire, right? Those free electrons will migrate to the surface in short order because they're being repelled by all the orbital electrons of the atoms of the copper wire itself. Okay? So in other words, this is a necessary, and then each one of these extra electrons also repels all the other extra electrons. And so they kind of spread out evenly with equal spacing in between them. Okay? And all of that can be deduced logically from just realizing like charges repel. All right, now concentration. Greatest concentration of charges will gather at the sharpest area of curvature. Anybody got a problem with that? Does that? What was the last slide talking about? Oh yeah, we just got done saying that the extra charges will spread out uniformly across the surface of the object. Charges will gather at the sharpest area of curvature. I thought you just said they spread out uniformly. What the hell is going on? Both of these can't be true, and yet they are, my friends. But those electrons are getting close. Wouldn't they be repelling each other? Why are they bunched up at the point like that on that bottom object? They should be repelling each other. You just said they spread out uniformly. I sure did. But they also concentrate, well, maybe saying definitively that they do concentrate at the sharpest radius of curvature is not the correct way to phrase it. And so, but first, let's talk about something else. Let's talk about Kansas. Which one of these is a picture of Kansas? Okay. And flat earthers can go pound sand, kick rocks. Yeah, get out of here. Okay. But yet, indeed, the picture on the right seems to be fairly flat. That surface is flat. But then you look, that's the United States, that's North America underneath those clouds there in the globe of the Earth. All right. Well, the flat earthers would say, well, that photo is a lie. But that's not the case. The Earth is a spheroid. It's an oblate spheroid. And so that means Kansas is curved. So what's going on here? Because the left picture gives you an idea that Kansas is curved because we know Kansas is part of the United States, and that object is definitely spherical. But the other picture with the buffalo, the bison, if you will, Kansas looks very flat, and I could see how a flat earther would be like, see? I love the flat earther videos. It's one of my favorite hobbies, just to laugh at these people. But yeah, there's a conundrum here. Kansas is either definitely round or definitely flat. How is it both? Well, perspective is relative to the observer, my friends. The reason there's apparent contradiction in rule number 3 and rule number 4 of electrostatics, or is it rule 2 or rule 3, whichever, distribution versus concentration. The reason there's an apparent contradiction is because you're not considering the size of the electron and how infinitely tiny it is. So this will break your brain. The electron has never experienced, if the electron had like a personality and had consciousness, it's never experienced a curved surface. No electron ever has encountered a curved surface. You say, what are you talking about? You bunch up at curved surfaces. And the electron will say, what is this madness you're talking about, curved surfaces? There are no such thing as curved surfaces. I have never seen, the electron's basically a flat earther. I have never seen a curved surface. If you had a, theoretical, if you had a conversation with an electron, I'm not sure that this is the way it would go. It would be more like, what the hell are you actually? So, but yeah, so that is a picture. See the gray picture next to the buffalo? That's a picture from an electron microscope of sheet metal. Okay? And the other one, that's a cartoon illustration of a cattle prod. But a cattle prod capitalizes on the rule of concentration along the sharpest radius of curvature. So what the hell is going on? What's going on is electric charge of a conductor is concentrated along the sharpest curvature of the surface relative to a human-sized observer. We're not saying that we say that it appears like the electrons are bunching up at the points of the cattle prod. What's really happening is the electron doesn't know that there's a point there. It is operating from like it's on the surface of Kansas. So there is no point there to the electron. So it doesn't know that it's bunching up. It literally is a perspective or relativity based thing. And only at the human observation scale does it appear that charges concentrate. It's an illusion. There is no concentration of charges, okay? But cattle prods work, and the charge is distributed from the point. So I won't play this video during the recorded lecture, but I am going to play it live for my students because I love Sherlock Holmes, and he incorporated a cattle prod into this fight. Masterful, and it's funny, so funny. Oh, not playing it. All right. So laws of electrostatics. Movement. Only negative charges move along solid conductors. Charges move along surface of solid conductor. So this is more See, it says laws of electrostatics, and it says this is the fifth rule, but this concerns charges in motion. So, is it really a rule of electrostatics, or is it a precursor to electrodynamics? Yeah, this is more as soon as you allow the charge to move, then you're not dealing with electrostatics anymore. You're dealing with electrodynamics. Okay? But why do these things happen? Why only the negative charges move along solid conductors? Oh, well, that's Newton's second law of motion. We see the smaller object accelerate when a force is applied. Charges move along the surface of a solid conductor. Oh, that's rule number one. Like charges repel. The conductor is made of atoms that have orbital electrons, and so the loose electrons must ride on the outside of the wire. Okay? And so, yeah, straightforward. But again, that's movement of charges. And so, aren't you really talking about electricity and conduction of electricity at that point? Yes, you are. All right, so Coulomb's law. That's equation one. So we have a force, an electrostatic force that manifests when you have distance between charges. Okay? And so electrons are charged, and so they would be either QA or QB in this version of the equation, Q1 or Q2. One of those would be the electron. So the Coulomb force says that when there's other charges in the neighborhood of an electron, that electron is going to experience a force. Imbalance of forces creates the opportunity for acceleration. And acceleration will manifest when a mass, like the electron, experiences an imbalance of forces. Okay? Remember that acceleration is the difference in velocity over time. And so that means the electron develops a velocity that it didn't possibly possess before when a Coulomb force acts on it. If it develops a velocity, it's going to possess kinetic energy because we already said it has mass. It's a particle. Okay? And so electrons that are acted upon by unbalanced Coulomb forces develop kinetic energy. That's what we can conclude from combining these four equations. I'll say that again. Electrons that experience unbalanced Coulomb forces will develop kinetic energy. They'll start moving and they will have the energy of motion. And that explains electricity, ladies and gentlemen. All right, Van de Graaff generator. I can't really do these well recorded. Okay, this is meant to be a live demonstration. I do have a Van de Graaff generator at the school. If you are attending X-ray school and your physics teacher does not have a Van de Graaff generator, tell them they really ought to pick one up because it is so easy to demonstrate electrostatics and the rules that we just went over, and it makes for a fun visit. Everyone likes playing with a Van de Graaff generator. It's you guys know what a Van de Graaff generator is. It's this thing. It's the charged dome. You've seen it on YouTube, and so it actually is a mechanism that creates electrostatic charge and deposits that electrostatic charge on the inside of a dome. And so we got two combs, metal combs or metal brushes. We have a rubber belt on silicone wheels. Okay. And so the friction force between the silicone and the rubber creates polarity in the rubber, and that makes the rubber pull electrons off of the bottom comb. Okay. The motor spins the belt, but the comb with its fine points, because the electrons are going to concentrate at the sharpest radius of curvature, the comb or the metal brush, the electrons are waiting at the tips of those points. And the rolling past the pulley makes the rubber a little bit polarized, and it actually yanks electrons off of the metal. Okay. Now it says voltage there. You can connect that bottom post to ground, and that's how most Van de Graaff generators are actually designed. Just connect it to ground, the ground wire that's going to the motor, and it'll still work. Okay. So those electrons rush up the rubber belt where they meet another silicone pulley and another metal comb. The second metal comb is that is connected by a solid metal, uninterrupted metal connection to the inside of the dome. And so we start stacking electrons. The dome tries to ground out the rubber belt. And so we start stacking electrons on the inside of the dome. And so the outside of the dome starts acquiring a positive charge. Okay. And so the end result is the dome starts to become charged over time. The longer you run the Van de Graaff generator, the more charge the dome collects. And you can get extremely high voltages with these. I think I've got a 125 kilovolt Van de Graaff generator. Now the amperage that it generates is minimal. It's micro amperage. And that's why it's safe. You can touch it and it's not going to stop your heart. It'll shock the crap out of you. Ask me how I know. But it won't ever stop your heart. It's great at delivering a static charge though. So just to complete the reaction, the grounded rubber belt that has just shed its extra electrons heads down on the other side to pick up more. Okay. And so the longer you run the motor, the more static charge builds up on the dome. So this was actually used as a source of, it was used for a source of electrons in several early physics experiments dealing with atomic theory. And so they used it as a particle accelerator, or just a particle reservoir, so to speak. But it has since the invention of the cyclotron and other physics experiments apparatus, the Van de Graaff has just been relegated to high school science classes. All right. So experiment number 1, balls made from aluminum foil come in contact with the Van de Graaff. Observe their behavior. What forces are acting on these little foil balls? Are they accelerating? And I think I do have these Van de Graaff experiments recorded elsewhere, unless I deleted that. I'm not sure if I deleted that or not. But I did have them recorded. I might still have them on the shared drive at the school. They might still be on the YouTube channel. They might not. I might have deleted that video. I'm not sure. Hang on just a second. So we're conducting the experiment on Earth. So gravity, yeah. The aluminum foil has mass, and so gravity, that's why it's resting on the bottom of the cylinder. Okay. Cylinder is made out of polymer plastic, and then it has a metal bottom and a metal top. The metal bottom is connected to the dome. The metal top is just in contact with the room air. Okay. Then we turn on the Van de Graaff generator. Okay. What's going to happen to the aluminum balls? When we turn on the Van de Graaff generator, we're going to start stacking charge on the dome. but the dome is connected to the floor of the cylinder by continuous metal contact. So the floor of the cylinder is also going to start stacking excess charge. And the aluminum balls are in direct contact with the floor. So it will start stacking charge too. Is it going to be all charges of the same sign? Yes, it is. And so the aluminum foil balls will acquire positive charge. The floor of the cylinder acquires positive charge. Now how many forces? Now we have gravity, but what else? That's right, we've got electrostatic repulsion, the Coulomb force, between the aluminum foil ball and the floor of the cylinder, right? And you really just have to, this recorded video doesn't do it justice, okay? When I stick my hand up close to, I don't have to even touch the top of the cylinder. I just have to stick my hand close to the top of the cylinder. That's when the magic really happens. Okay. And so I'm not going to reveal the last of this experiment, but it's definitely a repulsive force overcoming the force of gravity that makes the aluminum balls hover inside the cylinder. But then I'm not going to tell you what happens next. All right, the hairs on my arm stand up as I draw it close to the active generator. So I turn the generator on, and then I roll up my shirt sleeve, and I'm not a weightlifter, so I don't shave my forearms. And as I bring my forearm close, the hairs on my arm stand up. Okay. Why do they do that? Why is my entire arm not pulled into the vent? Sorry about that. I had a code here at the hospital. Why is my entire arm not pulled in by attraction? Why only the hairs on my arm? I've already explained it to you. It's one of the rules. Okay. What's the relationship between the force and the distance? That is, as I bring my arm closer and closer, do I get more hairs or less hairs to stand up? Why do you think that is? Okay. Also, one of the rules. Okay. Remember how force and distance are related for the Coulomb force. Okay. Go back to the equation. All right. If I place my hand on the generator, let's say the generator's grounded out, doesn't have any extra charge on it, and then I put my hand on the dome and then I turn it on, will I get shocked? And why or why not? Okay. After turning it on, the hairs on my head, or maybe even the hairs on my arms, start to stand out and spread out from each other. Why is that happening? Why do we see the effects in the hairs on my arm first, or the hair on my head? So these are all good questions, right? And we'll walk through them and discuss them together when I'm doing the demonstrations. All right. Those of you recording, I'm just going to skip through these, but I'll give you like 5 seconds to read. Okay, and then this is the results of experiment number 2. Okay, see how close you were to guessing the reasons why. And then this is experiment number 3. All right, and those are the Van de Graaff experiments that I typically run to demonstrate the rules of electrostatics and electrified objects and how they behave. All right, so how does an object become electrified? Well, friction, which is the abrasion of two conductive materials or two rough surfaces, basically. It works best with certain pairs. Okay. Contact, physically touching a charged body to a neutral body, creates a transfer of charge. And then induction, bring a charged body in close proximity to a neutral object without physical contact. It creates a charge on the neutral object. All right. Well, friction occurs, of course, when one object is rubbed against each other. Um, the At the atomic level, the outer shell electrons are being stripped off of the atoms of one of the materials and deposited onto the other. And so, a good example of this is rubbing a balloon on a wool sweater, rubbing wool socks against a carpet of another material. Um, I think a glass rod and silk can do it. Several other combinations can do it. All right, contact is when you have a charged object touching a uncharged object or another charged object. So with contact, electrons are allowed to, if there's an abundance of electrons on one of the objects, they will take advantage of the opportunity to distribute. And even remember the distribution principle. Well, the electron doesn't know that it's two separate objects that are touching. Okay, just like the electron has no idea what the hell a curved surface is. And so if you make contact with like a doorknob and you have static charge on you, you will balance out your excess charges with the doorknob. Okay. All right. And then induction. If you bring a charged object close to an uncharged object, the orbital electron, so let's say you have excess charges on a balloon. If you bring it close to a wall, like say at a birthday party, the electrons in the wall actually recede back into the wall. They go to the other side of the atoms on the surface of the wall. And so you get like a pseudo positive charge appearing on the surface of the wall because you're repelling the electrons that would normally be uniformly distributed there. Okay. And that's how you can just rub a balloon on your hair and you don't need tape. You can stick it to the wall by this induction force. It's pretty cool. All right, so both conductors and insulators can acquire excess positive or negative charge. It doesn't have to be conductive necessarily. Rubber can become charged, and we'll see just a little bit. Rubber's an insulator, and so that fifth bullet point addresses the trouble with rubber becoming charged, like a balloon. Okay? Conductors can be returned to neutral charge by grounding, right? So the ground is an infinite reservoir of both positive and negative charge. And then, so therefore, if there's extra electrons on a conductor, the conductor can donate those extra electrons to the ground. Or if the conductor is positively charged, the ground can donate electrons to neutralize it. Okay, so in both situations, the smaller object gets neutralized by the larger object. And so ground is just a big object. Lots of atoms and therefore lots of available electrons to either donate or take on. Okay? The Earth is an amazing ground. The Earth grounds things out all the time. In fact, the Convention for Positive and Negative. Remember Ben Franklin, one of his inventions to stop citywide fires because they built the houses out of wood back in those days. Bricks were expensive. Was the lightning rod. The lightning rod is basically a grounding wire that you run up the side of your house. You bury the other end of the wire in the earth, and then you tether the conductive wire to a spear point, okay, because charges collect at the sharpest radius of curvature. So putting these little spear points, these little lightning rods all around the roof of your house, when lightning struck your house, it ground it out. It didn't set your roof on fire. Okay. Uh, it worked fairly good, actually. Okay. Uh, so insulators can be charged, but they don't ground out all that well. They're really stubborn about because they don't let the charges move around. Um, and so conductors allow charges to move around freely, and so they can donate or receive charges really, really well. But insulators, you can charge them, but it's really hard to get them uncharged. All right. And then the electroscope is a simple device that we can measure the amount of charge built up by capitalizing on the electrostatic repulsion. And we do have an electroscope here at the school, and I will be able to incorporate it into the live Van de Graaff demonstration. The first electroscope was just gold foil suspended from a metal rod that went through a cork, and then there was a sphere on the top of the metal rod, and then you'd put the whole device in a flask. Okay, and that was to isolate the foil leaves and separate them from the charged object. And so as the foil, the very thin, usually gold foil for an electroscope, as the foil acquires more and more charge, you notice there's two foil leaves. Well, if they acquire the same charge, they actually start repelling each other. And so the spread of the leaves gives you the magnitude of the charge, basically. And so it's a way to measure the strength of the electric charge by the amount of repulsion of those little delicate foil leaves. Now, the pocket ion chamber is actually an electroscope, and I think it uses like a thin wire of metal, and then it's got a viewing gauge. It's got a little lens that's looking at this thin piece of metal moving past a little gauge inside the pocket ion chamber. And so the more ionization the chamber takes on, the more repulsed this little thin strip of metal is, and it reads a higher dose count. And so, yeah, the pocket ion chamber is a mini electroscope. All right, so I've been talking about certain materials are good conductors, other materials are good insulators, and I've talked about how it's related to atomic theory and the valence, the properties of the material. You know, the periodic table of elements. Certain elements behave certain ways. A stone and a bucket of water are different. Well, some things are conductors and other things are insulators. Copper is a great conductor. Gold is a good conductor. Platinum is a great conductor. Okay. Those are all in the same family. Those are all in the same vertical column of the periodic table. Go look it up. Well, silver is in there too. Platinum might not be in the same family. It might be gold, copper, and silver, all in the same family. Okay. Um, Copper, I think, either has one or two valence electrons loosely tethered, low binding energy. Okay. So it's another way to say that it's got a low energy threshold for conductivity. Conductivity is after a certain energy beyond the valence band, the electron just wanders free amongst all the copper atoms. And so if you have a copper bar, you really have electrons like swimming around randomly in that copper bar. Okay. Same thing for a gold bar or a silver bar. Okay. Um, and that's because it's got the threshold for conductivity, that is the outer shell electrons just leaving the atom, is really, really low in materials like copper. Okay. Other atoms and molecules could be, a compound, have relatively full valence shells. Okay. Um, Rubber, glass, plastic, these type of materials are basically hydrocarbon chains. Glass is not a hydrocarbon. Rubber is a hydrocarbon polymer. Plastic is artificial polymer grown in a laboratory. Glass is, I think it's silicon dioxide, and it's covalently bonded and randomly oriented. Okay. And so the valence shells of all these materials are full, and they don't allow charges to wander around like copper does. It's basically, glass is like the opposite of copper as far as the behavior. Okay. Copper doesn't allow light to pass through it. Glass says, yeah, go ahead. Copper lets electrons wander through it. It doesn't really tether them down. Glass says those electrons aren't going anywhere. So, yeah, completely opposite behaviors between glass and copper. So, um, insulators are useful to us because we don't like to get shocked when we hook up electric circuits. And so we wrap our wires with insulating material. Okay. Right. And so whether material is conductive or insulating in its overall in its behavior is on the scale of resistivity. And I found this on the internet. You don't really, this is more electrical engineering and theoretical physics than it is radiation science, but it does explain the behavior of materials fairly well. It's basically a sliding scale, and glass, polymer, rubber, polymer foam, wood, yeah. Now, the thing that's missing clearly for me is non-distilled waters. Okay. And I would put that over on the left-hand side, not as efficient as metal and metal alloys, but definitely a better conductor than wood. Okay. And so salt water, does it conduct electricity? Oh, yeah, it absolutely does. So if you're in the ocean, let's say you're shipwrecked, or you've capsized and you're just floating in the ocean, you could die of electrocution if the sharks don't eat you first. Because if a thunderstorm comes over and lightning strikes the ocean surface in your proximity, salt water conducts electricity. You're going to feel that. All right. And then we have these funny things. So there's conductive materials on the periodic table, and then in another area of the periodic table, there's definitely non-conductive materials. So what's about halfway in between those two groups? Well, that's where you find silicone and carbon, but silicone. Silicone is a semiconductor. Well, what the hell is that? Well, if you adjust its conditions, then you can. It's got that middle conduction band. And if you could adjust its conditions, you could get it to conduct electricity. How would you adjust those conditions? Well, don't make it pure silicone. Put in a dopant, an impurity that either has one more valence electron than silicone or one less valence electron than silicone. And then apply a little bit of voltage. And the extra electron dopant donates its electron and allows it to wander. In other words, a small amount of electrons, not all the valence electrons, but a small amount, enough, do end up conducting. And then those dopants with an extra vacancy, that allows a place for a wandering electron to drop into. And so that also increases the conductivity. We'll talk more about semiconductors later when we tackle the X-ray circuit. All right, and so that was electrostatics, but starting to show you very, 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 very easily how we can get to, oh, well, in certain circumstances, we could have all the electrons in copper move in one direction. Yeah, we totally can do that. So there were four true rules to electrostatics, and then the rules about motions of charges on conductors. So a fifth pseudo rule. Um, and these rules are consistent and they're readily demonstrable by the Van de Graaff generator. Okay. And then we learned about the difference of conductors and insulators and the chemical property of materials called resistivity. Low resistivity, that means it's a conductor. High resistivity, that means it's an insulator. More on resistance later. And that's all I got. I'm heading to the house, guys. Take care.